Okay, make sure that you are taking some notes on top of your little worksheet. Okay, so in this unit 8, we're going to be doing exponential functions and logarithmic functions. These are going to be seen on your ACT. This is going to be the first time you see logarithms. It will not, however, be the first time you've seen exponential. So hopefully this is a review. First hour and second hour, people have said, oh yeah, this makes a lot more sense than I remember it making sense in the past. So everybody, exponential functions. Here is the form, you should be writing this down, of an exponential function. Y is equal to A times by B, where B is raised to the x power. Now, A is the initial value, or the starting point. You'll hear me say it both ways. That's where we're starting, our initial value, our initial amount. And then we're going to be taking that initial amount and we're going to be timesing by some growth or decay factor. A factor means multiplication. So it's going to be a growth factor if it's larger than 1, and it's going to be a decay factor if it's less than 1. And I'll explain how this makes total sense in just a second. Now, a couple things to understand with an exponential function. Even if they don't write parentheses, technically there is parentheses around b, and only b is raised to the x power. Only b is raised to the x. So it would not be appropriate to multiply a in and then raise it to the x power. A is not raised to the x power. Does everybody understand? Okay, cool. And b will always be what's raised to the x. Okay, awesome. So let's look at 5 and 6. It says, state if this is exponential growth or decay, and then we'll also find the y-intercept. So I'm going to put this into perspective for you, and hopefully it's going to make total sense. So everybody listen, so you're not just memorizing, but instead it makes sense. If we're starting with $2, there's our initial value or our starting point. If we're starting with 2 or $2, let's put it in like a real world example, then we're taking that $2 and we're timesing it by 1/2. Isn't it going to get smaller? Yeah, so it's decay, which makes sense because 1/2 is less than 1, making it exponential decay. Does that make sense? Okay, now think about it. If I do a 1 here, that means we're taking 2 and timesing by 1/2 one time. If I put a 2 here, then that's squared, which means 1/2 times 1/2, right? So that would be taking 2 and timesing by 1/2 2 times. Does everybody see? So then wouldn't it just get smaller again? And smaller. So it's literally starting at 2-ish, and it's getting smaller and smaller. Okay, cool. We'll come back to y-intercept. Let's look at number 6. So my initial value is 3. Now, I need you to understand something. The initial value will not affect your growth or decay factor whatsoever, okay? So our initial value here is 3. Our starting point's 3, and then we're timesing by 2. Won't it get larger and larger? Makes sense. It's growth. You're awesome. So you would say, this is how I kind of show my work. 2 is larger than 1, therefore it's growth. Now let's make sense of this. So if I plug in a 1 here, wouldn't that be starting with 3, we're timesing by 2 one time, putting us at 6. Awesome. And if I put a 2 here, then we're taking 3 and we're timesing by 2 twice, which would be 12. Does everybody see? So it's getting larger and larger. Okay, cool. All right, so you guys do, we gotta do y-intercept. So for all functions, we can find the y-intercept with algebra. For all functions, no matter what type of function, the y-intercept is when x equals 0. So let's plug that in. So we have y is equal to 2 times 1/2 to the 0 power. Now simplify that. 2 times what's 1/2 to the 0? 2 times 1 is 2. So we write these as xy points. We plugged in 0, we got out 2. 0, 2 is the y-intercept, yes. He's making an excellent connection. He is thinking in these contexts, he's thinking advancedly. He said, won't this always be to the 0, so can't I just ignore that and call my initial value the y-intercept? Yes, awesome, way to see that. You're right, very good point. So let's do that here. What would my y-intercept be then? 0, 3. Let's pretend you don't see what I'm talking about. Just plug in 0, that becomes a 1, so we get 3. Okay, you guys do 7 and 8. Ready, set, go. check the answer up here. So on 7, you should have said a 6 is less than 1, so it's exponential decay. It's getting smaller and smaller. Our y-intercept is plug in 0. 1 6 to the 0 is gone. So then we get a fourth, 0, comma, a fourth. And then same with number 8. Is everybody good? Yes. Yeah. This is me showing work so everybody sees why. Yes. Okay, cool. So now let's put this is honestly where literally you see this stuff in the real world all the time. Like this is one of the most applicable in real world situations. So we just learned exponentials have this form where here's the initial value and here is the growth or decay factor. Now when we're thinking about doing this with real world problems, we've got to think of B as a growth factor and decay factor, but to do the math, we have to write percents as like decimals. So we're actually going to think of our B as a percent of growth or a percent of decay, a percent that goes down. So everybody, look, because this confuses people a lot of times. So for example, this is what I mean by this. If I gave you $500 and I said to you, you are going to get a 20% interest rate every year, okay? So now to write that in its exponential form, we're starting with $500, and then here's what throws people off. You're gaining to 20%. Don't we need to get back the original 500 to begin with, to even just start back where we, to even begin where we started? So that would mean we're getting back 100% of the 500. Isn't that true? But now we're getting an additional 20%. Now as a percent, that's 120%, correct? Now from there, you would say, I have to take a percent and write it as a decimal to do math with that percent. So now everybody, this is how percents work. If I have 120, technically 0.0%, right? I can change that to the decimal form to be able to do math by moving the decimal 2 places. So I would get 1.2. Does everybody see? Which makes sense. So this means, okay, we're getting back that full $500, 100% of that, plus an additional 20%. Does that make sense? Okay, awesome. Now looking right here, losing 20%, a lot of people will then put a 0.20. That would be wrong. Here's why. We're taking $500, and if we're losing 20%, won't we get out 80% of that $500? If we're losing 20%, we're still going to get 80% of that back. But only 80%, because not 100%. Does that make sense? So you would have to do, you could think of it like this, 100%. We're now taking off 20%, which gives me 80%, which as a decimal is 0.80. Okay, cool. That's where people mess up. Okay, let's start. Number 9, let's just put this into real world problems. This is literally what you will encounter. And when you start buying homes, cars, when you start saving for your kids on college, it says you put $2,000 into a college savings account for 4 years. The account pays 6% interest annually. How much money are we going to have? So let's write out an exponential function has this form. Now let's plug in everything we know. How much money do we initially start with? So right, 2,000. What's my growth factor? It's going up by 6%. 106% is what as a decimal? 1.06. And then we're doing that for 4 years. So now we have y is equal to how much in the end are we going to get? How much money after 4 years does this 2,000 become? I put in your calculator, everybody, to make sure you can do it right. You should get $2,524.95. Now what's cool about this is you're able to then say, okay, so just by putting my money in this bank account, I can come back 4 years later with not doing any work, and I've now gained $524.95. That's a lot better than having the money sitting under your mattress, not getting any interest. Yeah. No, because with this one, it was decay, so there wasn't. But if it's growth, yes. Great question. Okay, how about you guys do 10? Ready? I'm not going to go through it. Just do 10. Yes. All right, you should be good. Okay, moving on to number 11. You invest $2,000 in a college savings account that pays an interest rate of 4%. You make no future deposits or withdrawals. The reason they throw that in there is because that would obviously change things. If the next year you take out money, you're not now getting interest on that money you just took out. Or if you put money in, now you're getting interest on more money. So if we just put the money in and don't do anything with it, what's going to happen in 3 years? So let's set up our equation here. Y is equal to, our initial value is $2,000. This is a growth factor of 4%. That would be 1.04 and then raised to the 3. So our money has now become 2,249 and 76 cents. 73 cents? Cool. All right, so that is better than nothing. Now here's what literally people have ran into in the past. So this doesn't sound pretty bad. In fact, if you can find a bank that gives a 4% interest rate, you tell me, because I'm going to go put my money there. But you'd have to be more investing in stocks type thing to get that high of an interest rate, but still. So how much money will you have in 18 years? So a lot of parents really do this. They, as soon as their children are born, they go and put in money into a savings account for the kid so that they can go to college with some money and pay for their college. Now, if you're not a very smart parent, because you're just going to say, okay, that's going to be plenty. 18 years, I'm going to have a buttload of money. Instead of doing the math, you might be surprised at the ending amount. Let's see if you're going to have enough money to send your kid to college. So you weren't a very smart planner, and now your kid can't go to college, and now they can go to a half a year of college. Yeah, roughly. They'll have to get a full-time job still. That's okay. But keep in mind, so now keep in mind, if you were to calculate this, you'd say, oh, that's not enough. Every year I'm going to have to make put $1,000 in, and then you can start calculating how much you would really end up with. That would take a little bit of time, but you could do it. Yeah, but this is the offer from the bank. You can't change your offer. Does that make sense? Okay, cool. Let's do this one's different. Okay, everybody, here we go. Suppose you invest $2,000 in a savings account that pays a rate of 4%. Now, here's where it's different. So this one on part A, it says, how many years is it going to take? How much time do we have to put in for the account to, in the end, contain $2,500? So this is going to be solving for a different variable. So in the end, we want to know how long is it going to take to reach this amount. So this is our ending amount. Our initial amount was still 2,000, and then our growth factor is 1.04. And don't we want to know how much time it has to go in? We don't know what X is. We don't know how much time it's going to take us to get $2,500. Does everybody see? So now from here, here's the problem. We do not, based on this problem, everybody listen carefully to what I'm saying so you're not confused later. Because we're trying to solve an equation, and X, what we're trying to solve for, is an exponent. We cannot solve using algebra that we know yet. We will learn how to solve this. It will take a logarithm. So instead, we're going to just use our calculator, because if you were in the real world, you could absolutely use a calculator. So we're going to solve this by calculator. So everybody go to Y1, type that function in. We want to know, when does this function equal this function? So in Y2, type in that, graph them, and then we're going to see where they intersect. Here's what you need to think about. If I'm graphing this graph and you can't see anything, it's because you're not thinking very good. We have a straight line clear up at 2,500, where our calculator needs to see that high up. So go to window. High is up and down. So go to Y max, and don't make it 2,500. Let's make it above that. Like, I don't know, 3,000. Now you can hit graph again, and if you can physically see with your eyes where they intersect, you are good. If not, you might have to change X max to see further to the right. So everybody hit graph now. Oh, look, there's the exponential. There's the straight line at 2,500. Do you see how I can see the intersection point? So now do second trace. Go down to intersect. It says first curve, it's on the line. So hit enter, we're good. It's going to do it for you. It says second curve. Notice it switched to the exponential for you. You hit enter again. It says, do you want me to guess where these intersect? Yes, you'll guess accurately. And boom, it landed in the intersection. 5.69 years. So you say, this is going to take me 5.69 years to reach an increase of $5,000. Or, sorry, $500, right? That increased to $500 for my initial value. Now here is what people miss on the ACT. They will trick you on purpose. They will have, I have literally seen this problem very similar. They will have this answer, 5 years and 6 months because of the 0.6. People choose that. A lot of people choose that. That is incorrect. You have to think about what this actually means. So you guys have to think a little bit. This is 5 years, yes, but then this 0.69 means 69% of a year. Well, how many months is that? 12 times, we only want 69% of that 12 months. So take 12 and times it by 0.69. Now we truly know how many months. So 5 years and how many months? 8 months. Now with those other decimals, you could then get into days. Right, you could keep going. You can know the exact second of the day when you will finally reach that $2,500. I'm only going to ask you to go up to months. Is everybody good? Okay, you guys do B. I'm not going to do it for you or with you. You'll 10.3. Everybody, x equals 10.3. Did you get it? No, that's very different. So you got to make sure you get 10.3 because 10.6 is going to be way different in months. So that's a huge difference in reality. So 10 years, how many months? You would do, that's 30% of a year. So take 12 times 0.3. How many months? 3 months. So that one lucked out and was the same, but they often won't. Okay, cool. Sweet. Okay, let's do 13. It says a population of this grows at a 1.2%. Now, this is where people in the last 2 hours started getting like weird thought processes because of the decimal. This is still a percent, everybody. Do you see that this is not converted to a decimal yet? This is still a percent. We can have decimal percents, so don't let it throw you off. This is a population of 120,000. So we're initially starting with 120,000, grows at this rate. Do not let it throw you off. I'm going to go off to the side and write this down. We are getting back 100% of that population, plus 1.2%. I have not converted that to a decimal. Does everybody agree? So that would be 101.2% still, correct? Now let's change that to the mathematical decimal. Move it 1, 2. So we're going to have 1.012. Now that makes sense. 100 and 1.2%. And that's raised to the 15 years. So this population, it didn't say of what? People, rabbits, snakes. So how many people would we have after 15 years in the city that started with 120? In fact, this is a true statistic. I heard it on, they were talking about it the other day. Our areas in Utah are growing like crazy. St. George is expected to grow at a rate next year of 300%. Yes. And then our areas in Salt Lake and like in the Lehigh area are expected to grow like 200 or something percent. It's insane. Yep. Okay, how many did we get? Perfect. Right, that's true. So we're not going to have a pair of legs walking around without a body, so we could, in the context of the problem, kind of throw out that decimal. Oh, I don't know why I put a $sign, just out of habit. Good point. Okay, you guys, let's see if you can do 14 without my help. Careful, people mess up on the rate when they're doing decreasing. Where people mess up is the decay factor. What is the decay factor? What is the decay factor? Which is? So you're saying 98.5% is how much we're going to get out back, right? So now let's change it to the decimal, which would be 0.985. Very good. Because that, guys, think about why that makes sense. You're taking this amount and you're only getting back 98.5% of that. It makes sense that it went down. So then raised to the 12. And you guys just write down the answer. I'm not going to write it down. You can use a calculator and do it. Go. It says, let's see if you guys can detect the student's error, which actually happens. This is a true. I added this one on here because I heard two people talking last year. It says, a classmate says the growth factor of the exponential function is 0.3. What is their mistake? Yeah. Yes. 0.3 is less than 1. It's a decay factor. Then you could even kind of explain to them, now let's, my friends, let me help you out here. If you take 15 and multiply by 0.30 to the first power, you're taking 15 and only multiplying by 0.3 is taking 30% of that 15. It went down. That's decay. You know what I mean? Okay, cool. Awesome. Way to see it. Okay, I want you guys to spend some time and do 23, 24. Make sure you're good before we move on to more story problems. It says, let's read the directions very carefully. It says, state if this is a growth, it says if it's based on what you're given, what is the growth or decay factor? So this says we're adding 45%. Now you can only add percent with percent. So we would say, okay, so if we're adding 45%, we're getting 100% back plus 45%, correct? Which is 145%, which is a growth factor of 1.45. Exactly. Awesome job. That's all we do. That is our growth factor. That's saying we grew by 45%. Okay, let's look at 26. This one takes a little bit deeper thinking, and you're going to be asked to think a little bit. So everybody look so that you can kind of do similar problems the same way. It says, in 2009, a lot of times, guys, when you start having big problems like this, kind of drawing yourself a little, picture helps. So in 2009, there were 1,570 bears in a refuge. Like, these bears were going instinct. Wait, what's the word? Freak. I'm struggling. Okay. What was it again? Extinct. Sorry. Yeah, and so they put them in a refuge. I called it a refugee first hour. Okay. Then in 2010, now the bear population, since they've been in this refuge, has now increased to 1,884 bears. We know it increased, don't we? Makes sense. It says, if this bear trend continues and the trend increases exponentially, how many bears are going to be in year 2018? So let's go through and figure out some things here. First of all, don't I need to know my rate? So let's set up a true statement. If we're starting with this many bears, that would be, remember, exponentials have this form. So our starting amount of bears was 1,000, not dollars, I don't know why I do that. Let me write below, 1,570. Now we don't know the growth or decay factor. We knew it grew, but we don't know that, B value. In the end, we have 1,884 bears. And then how much time was between 2009 to 2010? 1. Now, you're going to use algebra to get B alone. Every problem is going to be different based on the information they give you. Isn't this what we're solving for, not an exponent? We don't need to use graphing then, it's just linear equation to get B alone. Divide by 1,570, divide by 1,570. So then we have 1.2 equals B to the first, which isn't that 1.2 equals B. We just figured out our growth factor. It went up by 20%, didn't it? Yeah. That's the factor, straight there. Yes. It's because we're rounding. So if you want to be exact, you would have to write down that entire decimal. So we're just kind of getting like a rough, pretty good guess here. So now we'd say, okay, so now our true statement here is y is equal to, our initial bear count was 1,570. It's growing at a rate of 1.2. Now careful here, do not just plug in 18. What year did we start at? 2009. So how many years later is 2018? 9. That's what you got to type in, go. How many bears can we expect if this rate continues? 80,100. Oh, I was like, whoa, that's 8,000. Cool. Hey, I want you to do the rest of the story problems, 27 through 32. Go for it. Super cool. Go, but draw yourself a picture. So it says, look at 28 with me. I'm going to help you think through how to do it. Your friend drops a rubber ball from 4 feet. It then bounces. Think about it in like real world. Like what would isn't this what would model like what a ball bouncing would do? Smaller and smaller and smaller, right? I didn't drop perfectly, obviously. So now it says he dropped it from 4 feet high. The next bounce was 32.5 inches. Well, then it had to fall 32.5 inches. It says the next bounce was 22 inches. And so on. It says if this trend continues, what will it be on the 4th bounce? So look, this is my first bounce, right? Ooh. Let's read this though. It says, wait, we gotta think. So it says your friend drops a stone, What is the, okay, how high will the ball bounce on the 4th bounce? So here's my first bounce. Here's my second bounce. Third bounce. This is why drawing a picture helps. We got to be very careful. I think I've messed up on this one from in previous classes. So, yes. Nope. So we've got to go through and figure out our percent, don't we? So here, notice something, feet, inches. This needs to be in inches. So this would be 48 inches because 12 inches and a foot. So we initially start with 48 inches high. That's where we start, correct? On the next bounce, we were at 32.5 inches. Now we don't know the growth factor, but we do know that was after one bounce. Now solve for B. You see how that works? Solve for B. So you would divide both sides by 48. B equals 0.68. So guys, it makes sense. This is 68% of the original height. It bounced up 68%. Does everybody agree? Okay, cool. So now when we set this equation, we got to be really careful here. We've got to choose the correct starting point, or if we, depending on our starting point, is what we've got to plug in for the time. Do you want to start with 48 inches? Okay, so if we do that, we would go like this. Okay, so y is equal to, we're starting with 48 inches. We're going to call that our first initial value. Now our growth factor was, our decay factor more accurately is 0.68, isn't it? And then we got to be really careful here. It says on the 4th bounce, what would the heights be? Well, let's count. 1, 2, 3, 4, 5. Don't we need to plug in 5? Downs, won't this down be the same as the up? Yes. If you don't put in 5, you're going to get it wrong. Does everybody see why? The picture makes it a lot easier to make sense. So couldn't we have started here and then done 4? Yes, because that's the ups. Do you see how we have 5 downs? Which will be the same as the up. Okay, cool. So we got to plug it into the 5. Dang nabbit. I have done that wrong in every other hour. Look at you. Hey, what is it? 6.98 inches. Dang it. After all these years. See, I still discover new math things that I've done wrong in the past. My key's wrong, and this is my key I've used every year. So, sweet. I promise you this one's right. I just didn't think very advancedly till now, apparently. Okay, awesome. Hey, all right. Do continue on those in that section. Go, continue. Well, you got to really pay attention here because you're going to want to understand what's happening with these graphs so that when you're doing way more advanced ones next year in your pre-calculus course, you're not completely confused. You understand what's happening. So everybody, we look at these graphs from left to right just like we read a book. So exponential growth will be really small and then get exponentially larger. Decay will be from left to right. It started out really large and then got smaller and smaller as time went on. So everybody, let's look at number 17. You don't have a graph on yours, so you're going to just kind of go like this. Draw yourself a rough XY chart. Don't even put in like points. I just want you to watch. You'll be able to graph some exact ones on the front. So we're just seeing what happens here. So it says graph the exponential function. Now here's what's important. So we're going to plug in some points. Let's not use our calculator for just a second. Let's just think for a minute. So I'm going to plug in -2. Now everybody listening, if you have a negative exponent, it is not a negative answer. We know negative exponents takes and flips our base over a fraction. So this is equivalent to 1/3 squared. You see how that's still positive? Not negative. So that's 1/9. So we plug in -2, we got out a 9, which is not negative. Negative exponents will not be negative. It will flip it and make it a fraction. Still a positive number. It's a small number, but it's still positive. Does everybody see? Let's plug in -1. That'd be 3 to the -1, which is 1/3. We plug in 0. 3 to the 0 power is 1. If we plug in 1, we get 3. What is 3 squared? 9. Let's plot those points. So just draw yourself a rough, you don't need even XY chart. Just watch. We're going back to up barely any, up a 9th. Okay, so up barely any. And then we're going -1 up a 1/3. A 1/3 is a little bit larger than a 9th, so just up a little bit more. Over 0, up 1. Over 1, up to 3. Over 2, up to 9. And now I can connect the dots. It makes sense that it's exponential growth because 3 is larger than 1. And look, it's growing from left to right. Now think about it, you guys. If I was to plug in -3, I would get 1/3 to the 3rd, which is 1/27, which is getting smaller and smaller. So do you see, as the negatives get larger and larger, we just get a smaller and smaller decimal. So it's approaching 0. It's just getting so small, it's getting approaching 0. And I wanted to show you using your calculator. So everybody go to your calculator, go to y equals, type in 3 to the x power, and then change your window back to a standard viewing window. 3 to the x, 3 raised to the x. Okay, window. Okay, we don't even, yeah, let's change our window to a standard viewing window. -10 and 10, -10 and 10. So if you hit graph, yeah, we already knew that. We just plotted points. Let's go to the table of values. So I can really get you to see what's happening here. So starting at like 0, for example, we already knew, yep, it was getting larger and larger. But look, as you go into the negative direction, do you see how it just keeps getting smaller? Oh, now it's 0.037. Now it's even smaller, 0.01. Oh, when we plug in -5, 0.00412. Do you see what I'm saying? Just continually gets smaller and smaller. It's approaching 0. This e to the -4, remember, just means move your decimal 4 places this way. 0.0004. So it literally is approaching 0. That is the definition of an asymptote. A value your function approaches but does not cross. So if this is just getting closer and closer to 0 and never crossing it, we must have a horizontal asymptote at 0 here. It won't. It'll just keep, because no matter the negative, it'll just get closer and closer. And then if we were putting it in a real world context, you would say, okay, but so now out here it's so small, we'll just call it dang well 0. If we were like, you know what I mean. But yeah, essentially no. It just gets smaller and smaller. Hey, what's my domain? Where's it going from left to right? -infinity to infinity. What's my range? Zero to infinity, not including 0. Awesome. Yep, so good. We wouldn't bracket that. Good point. So it did, so it's approaching 0, but not including 0. Now our y-intercept is when x equals 0, so plug in 0. 3 to the 0 is 1, so you'd say 0, 1. And our horizontal asymptote is x is changing, notice, but y is always 0. You'd say our horizontal asymptote is at y equals 0. Now, fun fact, exponential functions that are not shifted will always have a horizontal asymptote at 0. And you'll see even no matter what, that's true. Let's look at number 16. So now we're dealing with the decay function because 0.3 is less than 1, so it's going to be decay. So then it's going to start out large and get smaller and smaller. So now I don't care at this point. I want you to just go to your calculator and type in 0.3 to the x and give me some decimal points so I can graph them. If you plug in -2, -11.1, okay, -1, 3.3. It's easier to graph decimals. Decimals are fine. So 0.3 to the 0 is 1. 0.3 to the 1 is 0.3. 0.3 to the 2 is 0.09. I want you to notice something. Didn't we start large, get smaller, even smaller? Oh, really small. Aren't we just getting closer and closer to 0 if you continue to scroll down? Yeah. So once again, draw in your horizontal asymptote at 0. And then plot points. We're going -2, up 11. -1, up 3.3. Over 0, up 1. Over 1, up barely any. And so on. So now we can just connect those dots. This one got smaller quicker. The decay factor was smaller, which made it grow, like it jumped quicker downwards. Kind of interesting. Domain would be -infinity to infinity. Our range would still be 0 to infinity. Our y-intercept is when x equals 0, so what would it be? 0, 1, and our horizontal asymptote is at y equals 0. Okay, one more, then we will go ahead and just let you graph the rest by yourself. Okay, number 18. This is going to be decay. Just saying. So 1/5 is less than 1, so it's decay. Now, once again, go to your calculator, just type it in, -2, -1, 0, 1, 2. So I just want the decimals again. 10. Is it a decimal? 10, cool. What's 1 at? 0.4, what's 2 at? 0.8. 0.08, which is different. Okay. Look, it started out at 50, jumped clear down to 10, dropped down to 1, then clear down to 0.4, then 0.08. It's approaching 0 again, isn't it? So notice all of these have had horizontal asymptotes at 0. Plot those points. -2 up 50, not going to graph it. -1 up 10, I can graph that. Over 0 up 1, look how quick, like, do you see how it's growing down quicker because this is bigger? Smaller, I guess, essentially. You get what I'm saying? Okay, and then over 1 up a little teeny bit, and then over 2 up barely any. Well, I can connect those dots and whoo, shot up there quick because it's exponential. Domain is -infinity to infinity. Range is 0 to infinity. On these ones that are not shifted, because next time we'll shift them, our y-intercept is when x equals 0, which is 2. 1/5 to the 0 is 1, so 2 would be what's left. And then our horizontal asymptote is at y equals 0. Are these making sense to everybody? And when x equals 0, it's at 2. Oh, I did put 1, didn't I? Ah! What in sound? Well, yeah, but it's the last hour, so it's going to have to do. It should have gone through 2. Shouldn't it have? My bad. Good point out. Way to point that out to me. Hey, finish. I don't think you need more examples, do you? No. Hey, sweet. Then finish up all the graphing ones.